Alright, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 5.3, which deals with electron configurations. The objectives of this lesson is to, number one, apply the Pauli exclusion principle, the Apu principle, Hunds Rule, to write electron configuration using orbital diagrams and electron configuration notation. And the second objective is to define valence electrons and draw electron dot structures representing an atom's valence electron. All right, so it will be helpful to have a periodic table handy in this case. So we start out here with electron configuration. And electron configuration is just saying or defined as the arrangement of electrons in atoms. Now, a more layman's term for this essentially is the address specifying where each and every electron is for an atom. Now, in a ground state electron configuration, they're going to occupy the lowest possible energy. Previously, we've talked about how when an atom gets quote-unquote excited, they bounce from one energy level to another. This is saying, hey, those electrons are not excited. They are in that lowest possible energy level. The other thing to note with these notes is that you should fill in the blanks to your notes with these yellow highlighted terms. Okay, so now what I have here, I didn't include this in your notes, but I do want to go over it, and that is this extended electron configuration, or extended periodic table. And so what I have done is I have inserted that F block, or those intertransition metals, into the specific location, and that is the lanthanide and actinide is actually inserted into the periodic table. And so just to give you a comparison purpose here, again, these are my intertransition metals, and so we've essentially inserted them back into the lanthanide and actinide series. Okay, so now what we are going to do here is, just for these purposes, I'm going to cross out what we have on the right-hand side, and I'm actually going to add He to this position here, okay? So helium is typically on the right hand side, but for these purposes we're going to add it to this slot here, and this will play a role into what we have here with this. So our electron configuration is a way, again, we can have a quote-unquote address for each and every electron. So what we have here is 4 different blocks of the periodic table. This first block, consisting of 2 columns, is known as the S block. Over here on the right hand side, these 6 blocks are known as the P block. The 10 columns here is known as the D block of electrons, and then down here where we inserted the intertransition metals, this is known as the F block. Now each and every electron gets a certain designation. And so I'm going to start out by writing the electron configuration of hydrogen's box, and this is 1s1. Now, you may be wondering, well, what does 1s1 really mean? Well, let's break this down here. So the first number here is the energy level of the electron. Then we move over here to the letter, and the letter will either be an S, P, D, or F, and this letter is the sublevel of the electron. And then our last number here that is written as superscript is the electron number in that particular sublevel. The other thing I should note here is that this e to the minus is just my abbreviation for electron. So if you see that, e to the minus is electron. Now, with this second box, we're still in the first energy level, so we get a big 1. we're still in the S subblock, so we get an S, but this time we get a 2 because it is the second electron in that S subblock. Now, just like reading a book, we would go left to right, top to bottom, so we go all the way to left in that first row. There are no other boxes, so we move down to the second box. Well, in the second row here, we have the second energy level. We're in the S subshell, and we start our numbering over again because we're in a new subshell. So this would be 2s1. Now right next to it, we'd still be in the 2s level, and this would be the second electron in that 2s level. Now again, we scroll over here to our P level, and this time we're still in the second energy level. We're now in the P subblock, and because we've shifted our P subblock, we need to restart our numbering. So that would become 2P1. Now we label this 2P1 all the way over here to the right, 2P6. So you can see the superscript number increases by 1. And so we have 2P1, 2P2, 2P3, 2P4, 2P5, and 2P6. Now we get down here to the third row, and now we're in the third energy level. We start over with the S block. Because we're in a new block, we have 3S1 to restart our count there. This second box would be 3S2. We'd come over here, we'd start with 3P1, and we would scroll all the way over to 3P6. Now we move over here to the fourth row. The fourth row is going to be the fourth energy level. Again, we restart numbering, so we have 4S1. The 4S2 would be our next box. And now we need to pause real quick because our energy level for our D block is no longer equal to the row number. Our energy level for the D block is row minus 1. So because we're in the fourth row, row minus 1, 4 minus 1 would be 3. We're in the D block, and we would restart our count at 3D1. Now this would scroll over all the way to 3D10. And then once we get back to the P level, our energy level goes back to being our equal or is equal to our energy level. So row equals energy level. So 4P1 all the way to 4P6. Okay, so moving on here to period number 5. Again, fifth energy level, we have 5S1, 5S2. Be careful here getting to the D block. It's row minus 1. So we have not 5, but 4 D1 in our first box all the way over to 4D10. All right, energy level becomes equal back to the row number here for our P block. So we start out here with 5P1, and we scroll all the way over to 5P6. All right, so now we're down to rows 6 and 7. Again, energy level equal to row for our S block. And now we run into another issue with our F block. Okay, so our F orbitals have a unique circumstances, and this affects our energy level. Okay, so our energy level is equal to not row minus 1, but row minus 2 for our F block. So we're in row 6. 6 minus 2 is 4. This first box would be 4F1. we would label all of these F block elements all the way to 4F14. Okay, so now and that's 4F14, 4F14 here. Now we get to our D block here, row minus 1. We would be at 5D1 all the way over to 5D10. We get to the P block here. Rho equals energy level, so this would be 6P1 all the way over to 6P6. Our 7th row, we would start out here with 7S1, 7S2. Be careful here because our F block is rho minus 2 for our energy level, so this would be 5F1 all the way over to 5F14. Again, the last box should be 14. Okay, 5F14, 1 through 14. Our energy level for our D is rho minus 1, so this would be 6D1 all the way to 6D6. Excuse me, 6D10. And then our rho becomes our energy level here in our final block. So we'd start out here with 6P1 all the way to 6P2. 6P6. All right, so what we have done here is we've identified each and every location or address for each specific electron. So now what we can do is we can actually write the electron configuration. So you may need to keep this handy along with the periodic table, and we move on to how we write the electron configuration. So number one, we're going to locate that element on the periodic table. And what that serves as a stopping point. Okay, so that's kind of our end point, our end game with that particular point. And then we are going to write the electron configuration by writing each and every subshell of electrons. Now, one thing unique here, you don't have to write a bunch of things like we just did there. We just have to write the number of electrons at the end of each particular subshell. So we will do that in some examples. And just so you know here, more real world here, we don't really get into it. But some of the D block elements, they'll steal an electron from the 4s level to be half filled or filled. And that's just kind of an exception to policy. And then, just like in math class, once we do it the long way, there is a shortcut method that we can use to write the particular electron configuration. So we get to our examples here where we want to write the complete electron configuration for these particular elements, and we start with phosphorus. So what we do is we identify where is phosphorus. Phosphorus is element number 15, and so that will be our stopping point. Now, how we write the electron configuration, if we turn back to our electron configuration periodic table that we just spent time filling out, we have to go left to right, top to bottom, and read until we get to our box phosphorus. So we ask ourselves, at the end of each sublevel, have we reached our element? Well, the answer is no for that 1s level, and so we just have to write all of those electrons in that 1s level by putting 1s2. Again, just like reading a book, you go all the way into the row 1. Well, there's nothing there. We go down to row 2. Okay, we ask ourselves, is phosphorus in that 2s level? Answer is no again, so we need all of those electrons, so it becomes 2s2. We scroll over to the 2p level and ask ourselves, okay, is phosphorus in the 2p level? No. So we need all of those electrons, so this becomes 2p6. Go over to the 3s level. Is phosphorus in this level? No. We need all of those electrons, so we need 3s2. Then we go to the p level. Okay, so the p level, we ask ourselves, is phosphorus in there? Yes, it is. All right. We ask ourselves, what box number in the 3p level is it? And we say 1, 2, 3. So we write down this last electron configuration of 3p3. Now, to double check yourself, remember, in this neutral atom, number of protons and electrons are equal. So that means that number, because phosphorus had an atomic number of 15, the number of electrons should also be 15. So we ask ourselves, 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 3 is 15. There's our double check, and you can always do this. Now we move down to silver, Ag, and we find ourselves silver is element number 47. And we do the same exact process that we just did for phosphorus, except we're going to go a little bit further because silver is element number 47. So we ask ourselves, is silver in the 1s level? No. Well, that means we need all of those electrons. So we have 1s2. Is it in that next block 2s? No. So we need all those electrons. Is it in the 2p? No. So we need all of those electrons, 2p6. Is it in the 3s level? No. So we need all of those electrons, 3s2. Is it in the 3p level? Nope. So we need all of those electrons. Is it in the 4s level? Nope, still not. So we need 4s2. Is it in the 3d level? Nope. So we need all of those electrons, 3d10, and be careful, we jump back to our energy level. Is it in the 4p level? Nope, ain't happening. So we have 4p6. Is it in the 4s level? No, still not. Okay. Now, is it in the 4D level? Oh, yeah. What box number? How about box number 9? So we write down our 4D9. And I've made a minor mistake here. This should be not 4S level, but the 5S level. All right? So make sure you correct that on your sheet as well. Now, what has happened, and whoop, I've made a big mistake here. I jumped my energy levels and went all backwards here. I flip-flopped some things. Okay, so it should be 5s2, 4d9. Now, technically here, this silver electron here would probably steal this electron to be 4d10, but we're not going to get that technical here, okay? Again, last two should be 5s2, 4d9. All right, moving on here because, again, we want to write the shortcut method. What we do here is this. We do not want to write all of that business here for each and every electron that we have. So we have a shortcut method because if we look up radium, Ra, we found it's element number 88. We do not want to do all of that business there for element number 88. So what we do is we go up one row and we go all the way to the right and find the first previous noble gas. So to write this down initially, we're going to put the first previous noble gas in parentheses, brackets. Now, what that bracket indicates is we have all electrons from that point or through radon. Now we ask ourselves, okay, we're at this point, radon, we go down to the next level and we continue the electron configuration or writing it just like we saw it. So we ask ourselves, is radium in that 7s level? Well, the answer is yes. It is 7s2 because it's in that second box. Now, bismuth, we do the same thing. All right, bismuth, Bi, is element number 83. Again, we don't want to write all of that business down, so we go up one row all the way to the right to find the first previous noble gas. First previous noble gas is xenon, so we put xenon in our brackets. What that does is it indicates that we have all of those electrons. We have all of those electrons up to that point. Now, we continue writing our electron configuration by just picking up after the 5p6 level. We already have that, so we go and we ask ourselves, okay, is bismuth in the 6s level? No. Is bismuth, and be careful here, is bismuth in the 4f level? No. So we need all of those 14 electrons, so we have 4f14. We ask ourselves, okay, is bismuth in the 5d level? No. We need all of those electrons, so we'd have 5d10. Is bismuth in the 6p level? Well, yes. What box number? It's the third box here, so we would have 6p3. All right, so moving on here, we can do stuff with this electron configuration. You may think, okay, we just wrote a bunch of letters and numbers down. I get some of it may be correlated to subshells and things of that nature. What's the point? Well, the point is we can do a lot of things with our electrons by visualizing them out or putting them into things that are better able to help identify where these electrons are and what they can be useful for. So we get into this idea here of these orbital box diagrams, which is using the electron configuration and more specifically looking at the electrons in those orbital box diagrams. Now, to draw these orbital box diagrams, we need to abide by 3 principles. So all of these have names for the scientists who identified these particular policies or these particular rules that electrons abide by when they occupy a particular orbital. So we get into these rules, and I don't need you to know the exact name, but I need you to be able to apply it. And so the APU principle says, hey, the electron is going to occupy the lowest energy orbital available. So we're going to start at the bottom and work our way to the top. What that's saying is, hey, there is an order to how electrons are occupying those particular boxes. Now, again, what we have to remember here is that each sublevel actually increases a little bit in energy. So you can see with this little picture here that the 1s level is the lowest energy, then it goes to the 2s, then it goes to the 2p, the 3s, 3p, the 4s, and 3d. Again, there is marginal energy difference here, but the 3d still has higher energy, and that's why we write that after the 4s level, and that's where that stems from there. What we're going to do is we are going to apply this. Again, I don't need you to know AVPU is this particular definition, but what I do need you to know is, hey, how are you going to apply it? But just in case you need the definition, it is located here. All right, so the Pauli exclusion principle says, hey, each orbital can only hold a maximum of 2 electrons. Now we'll get into this opposite spin business a little bit later, in fact the next slide, but we can only have a maximum of 2 electrons in an orbital. And really this is important. I know I have you write this down, but 2 electrons in a single orbital. All right, that is very important. Now we'll get into the business here about the up and down arrows with our Hunds rule. Okay, so our next item or our next rule here is Hunds rule, and it says, hey, electrons with the same spin must occupy each orbital in a sublevel before we add additional levels. So for example here, this is our 2p level. And each of these boxes represent adding an electron in the 2p level. So essentially, if you want to put electron on each of these, it's helpful to remember that, hey, we're adding the second electron, we're adding the fourth electron, so on and so forth in our boxes. Now, what is happening here is that each orbital must have an up arrow to represent an electron, and each orbital or box must have an electron first before you go back and you add those double electrons. So again, we'll apply this here in a couple examples, but we'll go through our steps first. Okay, so our steps to draw an orbital box diagram is this. One, you need to write out the noble gas electron configuration. Now for each subshell, you're going to need to draw particular boxes that we need. Remember, one box is equal to one orbital, and one orbital can only hold a maximum of 2 electrons. Then we need to abide by those rules and add those particular electrons. Okay, so let's go over a couple examples. So we start out here with silicon. Again, the first thing that we need to do is we need to add silicon, or we need to find silicon on our periodic table, and it's element number 14. And again, we write the first previous noble gas by going up and to the right. And so we're going to put Ne in brackets, and that indicates that we have all those electrons through Ne. Now what we do, again, we're at Ne, we're at our 2p6, and we continue writing our electron configuration just like we see it. So we have 3s. Is our Se in 3s? No. So we need 3s2, and then we have to get to 3p. Silicon's in 3p. It's the second box. So we write 3p2. Now what we do here, we have to watch this carefully. We have to draw the correct number of boxes for each subshell. So out to the side here, our S subshell is going to be represented by one box because it only contains one orbital. Our P subshell will always be given 3 boxes because it has 3 different orbitals. Our D subshell will be given 5 boxes because it has 5 different orbitals. And our F subshell will be given 7 boxes because it has 7 different orbitals. All right, so that's some good information that we have. And so we move on from here. So we have an S subshell, so we need to draw one single box, and we need to label it as 3s to identify it's a 3s subshell. Then we have our 3p level. We go over here, we need 3 boxes for our 3p, and so we have our 3p, and again, we label it so we know it's a 3p level. And then we have to look at our superscript to tell us how many electrons go in that boxes. Okay, so in the 3s level, there are 2 electrons. So what we do, we represent the first electron as an up arrow, and then what Hunds Rule says is, hey, each electron in that subshell must have an electron, which it does, and then we apply the Pauli exclusion rule, which says, hey, they have to have opposite spins. So the second electron is represented by a down arrow. Now in the 3p level, we have 2 electrons that we have to represent. So we start out here with the furthest box to the left with our 1 electron, and then our Hunds rule says, hey, each box has to have an electron before we go back and we add doubles. Also, they have to have the same spin, which means they have to both be up arrows. And I just draw these arrows as half arrows, just as a nature of habit. All right, so let's go through another example here. All right, so we have now fluorine, F. Fluorine is F. If we go up and to the right, our first noble gas would be He. And so our He represents we have all of those electrons up to that point. We again read the electron configuration. We ask ourselves, hey, is He in 2s? Answer is no, so we have 2s2. Is it in 2p? Well, yes, it is. It is in that 2p5 box. And so again, we ask ourselves, all right, we have a 2s level, so that means we need one single box to represent our s subshell. And then we have a 2p level, which means we need a set of 3 boxes to represent that 2p level. We ask ourselves, okay, 2s2 means we have 2 electrons for this 2s level. First one's up, second one's down. Boom, we've got 2 electrons. We move to our 2p5. 5 means we need 5 electrons in that 2p box. So we start out with always the up arrow in the left-hand box. Then we have to make sure each box gets an electron first before we go back and we add seconds. So we have 1, 2, 3. We have 2 electrons remaining. So our electrons remaining here is going to go down in this first box. So we've used 4, and then down in that second box. Now, we are out of electrons, so this last box would not get an electron. Again, you have to add all up arrows before you go back and you add doubles, okay? The other thing is, again, they all must be up arrows before you add that down arrow, and that represents the electron spin. Now, calcium, we again find ourselves, okay, what is calcium? Calcium is element number 20. You go up and to the right to find the first previous noble gas, which is argon. So we have argon, Ar. Then we ask ourselves, okay, is calcium in that 3s level? Why, yes, it is. Or excuse me, is calcium in the 4s level? While yes, it is. It's in the 4s2 level. We only need a single box to represent that we have a 4s level. We have 2 electrons in that 4s level, so we add 1 electron with an up arrow, 1 electron as a down arrow. The most important thing here is, hey, we have to add electrons in order. The number of electrons in those boxes are represented by your electron configuration. And then you have to add electrons in each box before you go back and you add doubles. All right, so again, moving on here, we have one more concept here, and that is talking about valence electrons here, or Lewis structures. All right, so with this, we have valence electrons, and it says here that these are defined as electrons in the atom's outermost orbitals, or in that highest principal energy level. So what we could do here is we could do all the electron configuration for each and every element, but that would take quite a bit of work. So what we have developed, and what's really nice about our periodic table, is it's set up so we can find our valence electrons for our representative elements. So in our first column here, with hydrogen all the way down to francium, we have 1 valence electron. Now, V e to the minus is just equal to our valence electrons. Now, our second group or second column would have 2 valence electrons, and we skip over the transition and intertransition metals, and we go to boron's group all the way down to thallium. These would have 3 valence electrons. Carbon would have 4 valence electrons. Nitrogen's group would have 5 valence electrons. Oxygen's group would have 6 valence electrons. Fluorine's group would have 7 valence electrons. And our noble gases would have 8 valence electrons. So when I do this here, again, I am representing each column, the up and down column here, to have those particular numbers of valence electrons. Now you may need to keep this handy as we go over some particular examples here with our Lewis dot structures. Okay, moving on here, we get to this. Lewis dot diagrams are a way that we can represent a particular number of valence electrons in our element that we're looking at. So to determine the number of valence electrons, what we're going to do is we are going to have the symbol. We're going to look it up, and we're going to see what column it is in. Now, what column it is in will determine how many valence electrons we have. And I'll show you how to do that. But once we use or find our number of valence electrons, we surround the number of valence electrons by putting dots around our element symbol. So our element symbol is going to have 4 distinct sides. Now, each side must get an electron before you go back and you add doubles. Again, each side must get 1 electron before you go back and you add doubles. So we move here to our final examples here, and we get this, all right? We want to find the Lewis dot diagram for each of these particular elements. So the first thing we have is magnesium. Well, magnesium has the symbol Mg. And I should have started off with, we always write the element symbol right there. And then we ask ourselves, okay, what column is Mg in? Well, it's in the second column. That means there's 2 valence electrons. So for Mg, we have to have 2 valence electrons. That means we represent magnesium valence electrons with 2 dots. Now, it does not matter where you start with the dots. I always start at the top. But each side must get 1 before you add doubles. So you go through and we add 2 dots. Now, you could have put the dot below. You could have put them on the side. As long as each side has 1 electron to represent the number of valence electrons. Again, magnesium had 2 valence electrons, so we represent those with our 2 dots. We move on to sulfur. Sulfur has the element symbol of S, so we write that down, and we ask ourselves, okay, what column is sulfur in? Well, it's in this column that has 6 valence electrons. So we have 6 valence electrons, and so what that means is we need to represent, or we need to show that sulfur has 6 valence electrons by putting that number of dots around sulfur. Now, it doesn't matter where you start, but each side must get an electron first before we go back and we add doubles. Okay, so at this point here, we've used 4 of our 6 valence electrons. We need to add 2 more. Now, it doesn't matter where you put your doubles. I'm going to go around the horn again and just put our 2 additional valence electrons here. And remember, key thing is that each side gets 1 dot first before you go back and you add those seconds. All right, last one here is bromine. Look up the element symbol for bromine. It's Br. And so we have Br. Br is in that up and down group or that column with 7 valence electrons. So we have 7 valence electrons. This means that Br needs to have 7 dots around it to represent those 7 valence electrons. Now, we have 1 electron or 1 dot per side before we go back and we add pairs. Again, doesn't matter where you start, doesn't matter where you start with seconds, as long as each side gets 1 before we go back and we add doubles. So we have 3 remaining. I add my 3 electrons, and so bromine's electron or valence electron Lewis dot diagram would look like this. Again, each side needs 1 before you go back and you add doubles. Hope you have enjoyed this particular episode. This concludes not only section 5.3, but chapter 5. And as always, if you haven't done so already, make sure you subscribe.